as I started to announce our next presenter, it's Gisela Vega from University of Las Palmas de Gran Canaria. Again from Spain. We have a really strong team in today's first session from Spain. And Gisela will show us something about application of simulation, I should say, or finite element analysis in medical field or in additive manufacturing of molds, of models or parts for a medical field. So Gisela, please.
Thank you, Damir. Good morning, everyone. I'm Gisela Vega from the University of Las Palmas de Gran Canaria in the Canary Islands, and I will present modeling methodologies for finite element analysis of polymeric scaffolds obtained by additive manufacturing. After a small introduction and exposition of the objectives of my work, I will explain the modeling methodologies used, their description and steps, and I will conclude with the results of the practical applications and the conclusions drawn from them. Additive manufacturing is one of the most promising technologies for tissue engineering applications due to the high range of biopolymers that can be processed, and the 3D printing process allows manufacturing functional parts or tools from prototypes. And in the tissue engineering field, this process results in porous structures which are desired for cell growth and tissue regeneration. Moreover, the 3D printing process allows manufacturing complex geometries at a low price. However, as the final design of the deposited part is not available, the prediction of the mechanical behavior through numerical methods like finite element analysis is not possible. There are several ways to obtain the model of the printed part. In all cases, we have a CAD model. Then we convert this model in an STL file to obtain then the G-code file to print in a printer, in a 3D printer. And some authors prefer to model the solid part and then set the porosity in the slicer software. In this case, we can set the different patterns and different porosities, so we can obtain several porous structures from the same solid part in a simple way. But we cannot export the part with the filaments, and we cannot predict the mechanical behavior or simulate with numerical methods. Other researchers prefer to model the scaffold with filaments, so they have the model to predict the mechanical behavior and to optimize the part before printing it. But the porosity is already set in the geometrical definition of the model, and we cannot vary the pattern like in the slicer software. So it's difficult to design complex geometries. In this case, we also have problems with some slicer software because the method is not suitably defined. So some slicer software tend to interpret each filament as like a solid part. So it represents each filament like several filaments. In this case, in my work, the main objective is to find the best modeling methodology to reproduce the 3D printing scaffold from the solid part and optimize it, reducing the experimental work and improving the cost efficiency of the process. In order to achieve the main objective, it is required to reproduce the deposited part using different approaches. In this work, I compare two different approaches, the geometry-based and the model-based modeling technique. With the models generated, I applied finite element analysis and compare the results of the simulation in terms of accuracy, volume and dimensional accuracy, stiffness, and CPU time requirements. As previously mentioned, I compared two different modeling methodologies, the voxel-based and the geometry-based. The first one is done by a software called Volco, developed in the University of Nottingham, and it represents its filament as a series of voxelized spheres placed one after the other, taking into account the interaction of the filaments, resulting in an expansion of the joint, keeping the volume constant, as we can see here in the picture. And the second one, taking into account the plane, the swept path, and the assumed elliptic rectangular profiles in order to represent the different filaments. This second methodology was developed in this work. This is an article where we compare the two different approaches and select these two modeling methodologies in order to widely compare their limitation or their advantages. We also published our own modeling methodology, the CAD-based methodology, in the MathWorks file exchange, and is public if you want to use it. This is the diagram where I summarize the two different methodologies and their steps. In the first step, we have the G-code. It is a file generated by the Slicer software, and that can be understood by the printer. And with this G-code and MATLAB script, we extract the coordinates, having a matrix with 4 columns. The 3 first columns are the coordinates of the points, and the 4th column have values of zeros and ones. The 0 means that is the first point of the filament of the path, and the rest of the points are set as one value. With this coordinate, we can model with the geometry-based modeling technique, extracting the information of the plane, the paths, and the sweep generation, and then writing a Python file that can be imported in Abacus, a finite element analysis software. And after that, we can obtain the model in the Abacus software. This model, we can measure the volume and the dimensions. And after that, we can define the material properties. In this case, in the scaffold, we select the PCL material, the mesh type, which we mesh this scaffold with tetrahedral mesh, a quadratic or a linear tetrahedral mesh, and the boundary conditions. In this case, we have a displacement on the top face, and after that, we obtain the results of the simulation, obtaining the reaction forces in the base phase, and calculating the jam modulus of the part. So we know the stiffness of our model. On the other hand, in the voxel-based modeling technique, we also start from the G-code and the coordinates generated, and with a setup program. This is the voxel software, from the toolpath and the work area, the sphere radius, and the size of the voxels. This software generates an STL file. We can observe here that with the information of this STL, in particular the volume, we can adjust this volume to be the same than the theoretical. The theoretical is extracted from the G-code, and with an spline function of MATLAB, we can adjust the sphere radius, and obtain a new volume until we have the same volume on the STL file and than in the theoretical. With this STL file that we can observe that is a voxelized model, we can import this STL in Abacus and follows the same process than in the other methodology, setting the material properties, mesh type, and boundary conditions, and obtaining the reaction forces on the base and calculating the jam modulus. In order to assess the limitation and advantages of these two methodologies in the scaffold applications, we defined two different configurations. The first one is a square prism scaffold with a rectilinear pattern and a 50% of porosity, and a second one that was a cylindrical scaffold with different pattern and different porosity. In the first applications, we have this result. We have the results of the geometry-based model, the voxel-based model. We compare these results with the theoretical extracted from the G-code in terms of volume, dimensions, and porosity. In terms of dimension and porosity, it is quite similar, near to 13 millimeters side and 8 millimeter high in both cases, and the porosity is near 50%. But in the case of the volume, the geometry-based and voxel-based model volumes are similar, but quite different to the theoretical. But we can see that is near to the theoretical. And in terms of stiffness, the results of the jam modulus is too different if we compare the two model results. in the case of the voxel-based model, is almost the double of the geometry-based one. In order to compare with another application with other geometrical part, and also to compare if the pattern or the porosity are relevant in the results, we also simulate the cylindrical rectilinear pattern with a 50% of porosity scaffold. And here we can observe that the dimensions of the models are similar to the theoretical. But if we compare these dimensions with the experimental one, the printed part is too different. The volume is almost the same. And in terms of jump modulus, we can observe that it's too different in all cases. Any of the models cannot predict the experimental results. The same scaffold, but with a 60% of porosity, present almost the same results. The dimensions of the models are similar to the theoretical, but not to the experimental result. And the jump modulus of the models cannot predict the jump modulus of the printed part. And in the last configuration, we use a complex geometry, a gyroid pattern with a 50% of porosity. And in this case, we can observe the same that occurs with the other configuration, but in the case of the geometry-based model, it presented problems, meshing problems. So we have to mesh this part with a linear mesh to obtain a simulation, because if we mesh with a quadratic mesh, tetrahedral mesh, problems arise and we cannot simulate the part. Here, what we can compare the volumes that are similar in the case of the first configuration. In the second one, we can observe low variance in the experimental results, and maybe more significant in the last configuration, in the complex configuration of a gyroid. In the case of the stiffness, we can observe that any of the models can predict the experimental results, but we can observe that the gyroid is have the lower stiffness, and the first configuration is the higher one. The same occurs with the voxel-based model and the experimental, the printed part. So we can conclude that the results are not proportional, but the models can't predict which part is the most rigid part and which one is the less rigid. This is one of the conclusions of the work, that the jump modulus values of the models follow the experimental pattern. The most rigid model corresponds to the most rigid part, but not proportional. In addition, another conclusion is that the geometry-based model is faster and more computationally efficient in simple geometries, but it is also present more meshing problems in complex geometries. So if we want to model a simple geometry with high dimension, we will choose the geometry base. But if we want to model a small part with complex geometries, it's better to choose the voxel-based modeling technique. Moreover, the voxel-based modeling takes into account the filament interaction during the extrusion process, so the model is more realistic compared with the deposited part. And in terms of volumes, the geometry-based model volume is close to the theoretical one, while the volume of the voxel-based modeling, of the voxelized model, is the same of the theoretical, because we are manually adjusting the volume with the spline function. Currently, we are working with these results in order to optimize the scaffolds before printing them, and taking into account other parameters important for cell growth and tissue regeneration, like the porosity, pore size, and interconnectivity of the holes. So I conclude my presentation. Thank you for your attention, and thank you, Damir, for your invitation to the summer school.
Thank you, Gisela, for an interesting presentation and for your support to our project. It was very interesting for those who will go a little bit more in deep in order how to create more parts with higher properties, target properties, which is sometimes very important, especially in medical sector, but also in some other sectors. It's not only for a medical application. Thank you very much once again, Gisela. Is there any? We have maybe one question. I will. You have one thing from Misa. Yeah, because she's also an expert in modeling for materials. We saw that. Okay. There is a question. Okay.
Okay. He's asking how long it takes to run the simulation. It depends on the part and the number of elements. But in Abacus, I try to reduce the simulation time, only calculating the reaction forces, the displacement and stress in the base phase, and only the last increment. With that, we can obtain the results of scaffold with 2 million nodes in 1 hour, in around 1 hour.
And we have another question from Misat. Gisela, can you see it? What is the agreement between simulation and experimental data if you have carried out experimental trial?
I don't know if you are if you are asking for the JAM models of these results of the models are the experimental, are the simulation results, and this one that says experimental is the printed part results. So the agreement is, as I said, we cannot predict the experimental results. So in the optimization methodology, I take into account this in order to optimize the deposited part. with the model's results, the simulation results, taking into account that it's not the same. Applying a correction factor.
Okay.
I don't know if I answered the question.
I hope yes. Again, one small question.
It depends of the because depends of the case, because in the 50% of porosity and rectilinear pattern is closer to the geometry-based model, and in the case of the gyrate is closer to the voxelized model. So, but in this case, in scaffolds, after the comparison of methodologies, we will only use the voxel-based methodology. So we can only use the results of the voxelized model, the voxel-based methodology, to predict the experimental results.
Okay. Thank you. Thank you, Isra, for putting a question, and Gisela, thank you for answering all the questions from Isra. So we are now near to 12, near the noon, according to our time, and that was upon our agenda, time for a short break. So thank you all of you for patience during this and attention during this morning session, and thank you for all presenters to share with us their knowledge, their experience from this very specific, but I should say very attractive and very interesting field, which will be more and more important in the future when these additive manufacturing technologies will certainly have more application in areas like medical sector. So if someone of you will not be present with us during the afternoon session, I would like to wish a Merry Christmas and Happy New Year to all of you. But I hope that we will stay together after 15 minutes break in very interesting presentations from afternoon presenters. So I'm inviting you to come back in 12:15 when we will proceed with afternoon session. Thank you again for all of you, and see you in 15 minutes. Bye.